With the core concepts of RL in mind, let's explore a fundamental and widely used algorithm, Q-learning. This algorithm helps an agent learn the optimal action value function, or Q function, which directly tells it the best action to take in any given state. Q-learning is a model-free and off-policy algorithm. Model-free means it doesn't need to know how the environment works, the transition probabilities, or reward function. It learns purely from experience. Off-policy means it can learn the optimal policy while following a different exploratory policy. The core of Q-learning is iteratively updating the Q values in a table, the Q table. Imagine a table where rows are states and columns are actions, and each cell stores the Q value for taking that action in that state. Initially, all values are 0 or random. When the agent takes an action, it observes the reward and the next state. It then updates the Q value for the action it just took using the Bellman equation. The update rule considers the immediate reward and the maximum Q value achievable from the next state. This means it learns not just from immediate gratification, but also from the potential future rewards. This iterative update, often done with epsilon greedy exploration, where the agent mostly exploits its current knowledge but occasionally explores new actions, allows the Q values to converge to their optimal values over many interactions with the environment. Once the Q table is learned, the optimal policy is simply to choose the action with the highest Q value in any given state. However, Q tables only work for environments with a small, finite number of states and actions. What if your environment has millions or even infinite states, like a complex video game or a continuous control task? This is where deep Q networks come in. DQN integrates deep learning with Q learning. Instead of a Q table, a neural network is used to approximate the Q function. The input to the neural network is the state, and the output is the Q value for each possible action. The network learns to predict these Q values by minimizing the difference between its predictions and the target Q values from the Bellman equation. DQN, popularized by DeepMind's success in playing Atari games, revolutionized RL by allowing it to handle high-dimensional observations like raw pixel data from a game screen and much larger state spaces. It opened the door for RL to tackle real-world complex problems. Let's look at more applications of reinforcement learning.